we're going to look at the normal approximation to our binomial distribution. See, if we've got this sort of question, a school of 1,200 students, much like our own, contains more than 150 left-handed students. That's what we want to find out. What's the probability of this? So how would we solve it? Well, we could take a sample. If we get a nice large sample, it'd be approximately close. So let's say we pick 50 people and we'll physically count the number of left-handed students, and then from that we could estimate the probability. So basically we're taking a sample rather than a census. Now let's say our sample we picked had 8 left-handed students, and from that we would estimate the probability then is 8 out of 50, 0.16. That would seem a logical thing to do. Now, using binomial probability then, we'd say, well, X is going to be the number of left-handed students. It's binomially distributed. There's 1,200 students all up, and we've now estimated the probability of left-handedness is 0.16. We want to find the probability that X is greater than 150. Probably going to be easier to do 1 minus the probability of less than or equal to 150. Use the complementary idea. But that's still a heck of a lot of calculations to do, because I've got to work out none, 1, 2, 3, all the way up to 150. Certainly quicker than going from 151 up to 1,200. But there are a lot of calculations, 151 of them, in fact, to do. It does turn out to be that. 0.9996. Is it practical to do that when we're talking about such a large group? And the answer is, well, no, it's not practical to do that. The polygon looks like that, our normal. What we've just done is we've found the area to the right-hand side. Remember, the probability basically is the area under the curve. If we look at this distribution, it has a modal class somewhere in the middle. So, yep, the peak is somewhere in the middle of the distribution. It is symmetrical. It certainly looks symmetrical. Pretty close to it if it's not. The frequency density does tail off very rapidly as we go away from the mode. Now, they are all features of a normal distribution. So if we assume the distribution was normal rather than our binomial distribution, we've now got to work out what the mean and the variation is if it was in fact a normal distribution. We know it's binomially distributed with a sample size of 1,200, well no, not a sample size, it's the population size, isn't it? The population size of 1,200, and we've worked out our probability of left-handedness is 0.16. So I know that the mean, I can work that out, n times p, 192, and the variance is 161.28. So now I know those two pieces. If I'm now going to say actually it's a normal distribution, and the two things we were interested in a normal distribution was the mean and the variance. So we're now saying actually it's normally distributed with those pieces of data. But then what we saw with normal distributions, we like to standardize it so we can look up in our tables and find the values. So now we need to standardize that. We'll turn it into the standard normal distribution. Remember, our formula for doing that is our random variable minus the average divided by the deviation. So back to our problem. Our problem is we wanted to find the probability that X is greater than 150. I'll still use the complementary event idea. So 1 minus the probability of less than or equal to 150. I will convert that into our standard normal distribution. So Z would be less than or equal to 150 minus 192 over the square root of 161.28, which turns out to be negative 3.31. I can now go to our tables and work out the value, and it's not bad. Remember we worked it out before, it was 0.9996. We've got 0.9995 by assuming it was normal rather than binomial. How big a difference? Well, it's out by 0.008%. That's a pretty good estimate right there. And it's a heck of a lot quicker to work out than all of those individual pieces of data. Is it okay to always do this? Well, no, it's not always going to be okay to do it because remember we have to have those features where the mode's somewhere in the middle and all that sort of stuff. Now, we don't want to have to draw it up each time. But keep in mind those three pieces. The mode has to be somewhere in the middle. The distribution needs to be symmetric, and that frequency tails off very quickly. They're the three key things we're looking for in the graph. Let's look at some. Here's one where the probability is 0.125, and I've drawn different ones for where we've got a sample size of 10, 20, 30, 40, 50 and so on, and there's the different graphs. Now if I look at that and go, well, is it good or isn't it good? And the values I'm looking at are P, Q, NP and NQ, and then making a decision. So the blue one here, the first one's down, I'm saying, well no, it's no good because look, it just stops. So it's not tailing off on the left hand side, so that one would be terrible. Same as when it was 20, 30, 40, so the yellow one, I've put both a tick and cross on that one because you can see it's like, well, it's starting to tail off there. The last one though, 50, yeah, I'm okay with that because it tails off, and so what, I don't have all this past zero, it's going to be fairly flat. So I think the 51 looks okay. If it was 0.25, these would be the graphs. So this time now I'm happy with the 50, the 40 and the 30. I think they look all right. They satisfy the things we're looking for. 20, it's starting. Is it there or not? Don't know. But the 10 I'm still not happy with. Still not happy with the 10. 0.375 is what the graphs now look like. And so now I'm pretty much happy with all of them except the first one, n equals 10 I'm still not happy with. And if it was nice probability in the middle there, 0.5, yeah, I'm pretty much happy with all of those. The first one's close, so that's why I put a tick and a cross there. It's close, but yeah. The others I'm certainly happy with using an approximation on. Well, I don't have to physically draw these graphs each time. So looking at those key pieces of data, then what I can look at is in each of those, when I all of a sudden started to become happy was when n times p and n times q were both bigger than 5. So that's where, notice when they're exactly equal to 5, that's where I've gone, oh, hang on. Ooh, am I, aren't I? But pretty much if you look through all those tables, when they're bigger than 5, I've gone, yeah, I'm happy with that graph. So rather than having to draw the graph each time, I just look at, well, NP and NQ, and then I can make a decision. Yeah, I'm happy to go with a normal approximation on this. Now, remember what we're actually doing is it's the area under the polygon. Our bins, as we call them, are 1 unit apart. So technically the area under the polygon is actually a minus 0.5 and b plus 0.5. If you think of the histogram, the actual rectangles, and that'll be a bit more obvious what the integral actually is. So when you have really small samples, there's this thing called a continuity correction. It's not a big deal to worry about, to be honest, but just to let you know, when they're small samples, then when we're finding the probabilities, rather than going between A and B, we might add 0.5 and subtract 0.5 just to get a better estimation. Not something, as I say, we should be worrying about, but that's what we do in stats. We have this thing called a continuity correction. So let's have a look at a couple of HSC questions. There's only been, of course, a few HSCs on this new course. So here's the one from 2021. We're tossing a biased coin. So the probability of a head is 3/5, tossing it 100 times. X is our random variable, the number of heads. This random variable has a binomial distribution. Find the expected value is the first question. Okay, well we know that's n times p, so we would expect 60 of them. Makes sense, probably these 3/5, tossing them 100 times, yeah, I'd expect to get 60 heads. By finding the variance, show that the standard deviation is approximately 5. Okay, well that's NP, well Q or 1 minus P, whatever you want to call it. So 100 times 3/5 times 2/5, 24. We want the deviation, however. That's 4.89. Yeah, that's approximately 5, and that's what's it. But it's approximately 5, so we've done that. But now, by using a normal approximation, find the probability that X lies between 55 and 65. So all right, we now know it's binomially distributed. Number of times we did the experiment was 100, and the probability of success was 0.6. That means my normal distribution, I'm going to assume, is 60 and 24. That's what we just worked out in the previous parts. But we want to standardize that get it to our standard normal distribution. So probability that x is in between 55 and 65 will become the probability of z. Oh, how nice. -1 and 1. Excellent. That happens a bit, I guess, because of the tables, but we also know that there's so many percent are in between one deviation and so on. So yeah, 0.68, because we know that 68% lie between those two deviations. We don't actually need to go to our tables for this one. Okay. Last year's one. Chocolate factory selling 150 grams chocolate bars. There's been a complaint that the bars are actually less than 150 grams. Team of inspectors go to the plant. They've got to check it out. They randomly pick out 16 bars and weigh them. And they found that, 8 of those 16 weighed less than 150 grams. Now, the factory manager's saying, well, hang on a sec, 80% of my chocolate bars are 150 grams or more. You've just picked a bad sample. You got unlucky when you picked that out. So, first part of the question. Inspectors then are going to use a normal approximation to the binomial distribution. They're very clever inspectors, they know their maths, to calculate the probability of having at least 8 bars weighing less than 150 grams. Was this unlucky, or was it, no, this is typical what's going to happen, don't try and tell me that you got more than 80%. So weighing less than 150 grams, a sample of 16, assuming the factory manager's claim is correct. So calculate the value of P. So X is going to represent the number of bars that weigh less than 150 grams. So it's binomially distributed. 16 bars is how many we're pulling out. The probability of it being less than 150, according to the manager, is 20% or 0.2. So that's the data we're going to use, and we're going to see, all right, are you telling me the truth? So the average then, n times p, will be 3.2. The variance is 2.56. So we're now going to say, all right, it's normally distributed with those pieces of data. We want to turn that into the standard normal distribution. We're trying to find the probability that there are actually more than 8, or equal to. Let's use the complementary idea, because you remember our tables go less than rather than greater than, so it's usually easy anyway. Chuck it into our z-score calculation, we get 3. And nicely that just turns out to be 3. 0.0013. So what did we just work out? We just worked out the probability of having at least 8 bars weighing less than 150 grams. That's what we just found out. And we're saying that probability is 0.0013. Hang on though, the factory manager goes, no. Hang on, look, we disagree. I think the method you used is no good. No, you can't do that. Is indeed this manager correct? Is it valid or not, what they did? And that then comes back to this idea of what is NP and what is NQ. Was it okay to use a normal approximation? Now, NP is 3.2. That's less than 5. So we'd say, well, no, actually, for a good approximation, we would like NP and NQ to both be bigger than 5. So actually, maybe the factory manager is correct, and the inspectors were the ones that did the wrong thing. It is unlikely that this method produces a satisfactory approximation to the probabilities. Okay, so 17C, look, to be honest with you, I can't remember why I've put that link there. It probably has something to do with one of the questions, that this could well be handy for comparing different approximations, but for the life of me, I can't remember why it's there.